So what I've done is I've kind of arranged a little presentation that's going to be close to some things that you're going to have on the test. It might look somewhat familiar. I can't actually use the exact same test questions, but I can go over things that are similar. All right? So talking about generating electricity. So this is one of those things where we have the conversion of energy from one type to another type. All right? So hydroelectric, that's going to convert kinetic energy of moving water into electricity. Windmills are going to have the same thing. You're going to have something that's going to be spinning. It's going to be using that kinetic energy. And with the use of magnets, it can actually convert kinetic energy into electrical energy. Okay? So all these things have one thing in common, and that is there is a turbine that spins from that kinetic energy, and that's what generates the electrical energy. All right? So these all have a commonality in that they spin a turbine. Looking at these different types of energy transfer, understand that convection, radiation, conduction, these things can all transfer thermal energy. Thermal energy is the speed of the molecules. It is the kinetic energy of the molecules that make up matter, and it's how fast they're moving. One thing about the energy that I want you to know, especially the transfer through convection, is that when it's warmer, it's going to rise to the top. This is what causes the even heating of this, let's say this is water. So the warm molecules are going to go to the top, the cold ones are going to sink down. And the reason that happens is because these are going to have less density than the cold ones. Okay? Now the opposite of this you can kind of see in the ocean. You know, the top part of the water is going to be warm, whereas the bottom part is going to be cold. And the reason for that is that in that situation, your energy is coming from top down. Here, it's going from bottom up. But just understand that the warmer molecules go to the top, whereas the colder ones are going to sink down. Now, one thing that kind of makes this different is that with conduction, you have to have direct contact. With convection, you just have to be close to it. Okay? So that was one that you guys kind of missed some questions about convection. But the idea here is that you do have these convection currents. Okay? Any questions about convection and how those move? Okay. So when we talk about sound, and right now we're looking at sound waves in class. We're getting ready to move into that. But when we talk about sound energy is going to be a kinetic energy. Because when that sound is emitted, it causes particles to vibrate. And it's that vibration of those particles and molecules that is the kinetic energy of matter. So basically the sound is emitted, it causes the matter to vibrate. For us, most of the time that's going to be air particles, and it's going to be transferred. Talking about chemical energy, and this is just dealing with what kinds of energy are really other kinds. So chemical is potential, and electrical can be potential or kinetic. It depends on whether or not something is actually operating. But sound is going to be a kind of kinetic energy. Yes, sir?
So for sound energy, it's it's kinetic, isn't it? Also creates thermal.
Well, remember that thermal is really kinetic also. That's where it can kind of get a little complicated. So just understand that when we give a name to a kind of energy, right? That's a name that we give that's going to describe what that energy is going to be used for. So if we say kinetic energy, that means the energy is going to be used for movement. If we say, potential energy, that means it has the potential to do something. It's not quite being used yet. So chemical energy, gravitational potential, elastic potential, all those types of energy that we call potential energies, that means it has the potential to do something else, that it's about to be used. So chemical energy is stored energy that can be, stored to use something. A battery is a great example of chemical potential energy. Okay? We also have a pine cone in a tree. That's an example of gravitational potential energy. Looking at this formula, kinetic energy equals half mass velocity squared. We talk about, how to, use this formula to calculate the kinetic energy. You got to think about this in abstract terms, though. If you're given this formula and you're asked, hey, what's going to happen if we double the mass? What's going to happen if we double the velocity or cut the velocity in half? If you don't know what's going to happen, go ahead and just set this up and give it numbers, and then do whatever you have to do to change the numbers. Like just give mass 2 and give velocity 2, and then calculate it, and then go ahead and double the mass like the question is asking you, and then calculate it again and see what happened. But, just so you know, if you double the mass, you're going to double kinetic energy. If you want to write that down, you certainly can. Okay? If you double velocity, you're going to quadruple kinetic energy. And why is that going to happen? Because you're squaring it, right? And so mathematically, you're going to have this other thing that's going to happen. All right? All right. The roller coaster stuff. Let me just kind of talk about that for a second, because these are really good questions, and I want to touch on this. All right, so when you're up here at the W, you have 100% potential energy. You have 0% kinetic energy. When you're down here at the very bottom, not there, but right at the very bottom, you're going to have 0% gravitational potential energy and 100% kinetic energy. So remember, energy is energy. We give it names according to what it's used for, right? If the energy is used for movement, we call it kinetic. So if I have, and then just an arbitrary number, let's say I have 1,000 joules of energy, then I have 1,000 joules of gravitational potential energy, 0 joules of kinetic. If I have 1,000 joules down here, I'm going to have 1,000 joules of kinetic and 0 joules of gravitational potential. Now, is that entirely accurate? No. Why is that?
Because
what happens when you change energy from one form to another? If I change from gravitational potential to kinetic, what is going to happen? Yes, sir?
Energy is going to be lost.
Right, so you always lose some energy when you have an energy conversion, okay? So it's not going to quite be 1,000 down here. I'm going to lose some due to friction. But it's not lost. What happens to the energy that's taken away? It's converted to thermal. Very good, right? So here's the thing. If I want to ask, like let's say right here, how much potential and how much kinetic do I have?
50-50.
50-50, right. So it's about 50% and 50%. Now, I can actually calculate a rough estimate of how fast I'm going right here. All I have to do is take the 1,000 joules, multiply by 0.5, and I'm going to get 500 joules. I can then work backwards and say, okay, that equals half the mass velocity squared, and I can solve for velocity to find out how fast I'm moving. I can do the same thing if I knew, so you have to know how much mass you have to do that, right? Because you can only solve for one variable. But given that, I should be able to solve for this because I would have to multiply by the percentage to find out how much of that 1,000 joules is going to be potential and how much is kinetic. Down here, maybe I have 80% kinetic and 20% potential. So down here I could multiply 1,000 times 0.8 to find out what would 80% of that energy be, right? So again, this is going to be an estimate, but your numbers should be pretty close to what you calculate. All right? So the idea is, again, like I just said, when you have an energy conversion, like let's say we have the skateboarder in the on the half pipe, okay? The amount of energy is going to be the same, but you're going to lose some due to that energy conversion, right? So as a person goes back and forth, they're converting energy back and forth. And it's going to create friction. You're going to have the increase of thermal energy. But overall, you're going to have the same amount. But remember, you have to take into account that some is lost due to that conversion, and also in this situation due to objects touching as they move. So these are the energy conversions that happen within a flashlight. Okay, so you have batteries. What kind of energy do batteries have?
Electrical.
Chemical.
Okay.
They have chemical potential. Okay, so hold on with that. But they have chemical potential, and then it becomes
Electrical.
electrical, and the electrical is used for
Light and thermal.
light and thermal. Okay, so again, some energy conversions take place. You have 3 different types of energy. Well, 4 really, if you think about it. But you're going to have an increase in thermal energy. If you were to touch the wires where the batteries touch the electrodes inside the flashlight, it's going to feel warm to you because you have some energy conversions that are taking place. Okay? Again, energy is energy, but we name it according to what it's being used for. Okay? What kind of energy is chemical, really? What kind of energy is chemical, really? Potential. Very good. And then electrical can be potential or kinetic depending upon what it's being used for. This is a catapult. How can I make this catapult fly farther? What can I do? If I pull this back and I want to shoot a marble across the room, what can I do to make the marble fly farther or faster or with greater force and speed? Yeah.
You could like take it back as far as possible.
Right, because when I take it back, I'm going to be converting, well it should be elastic potential energy. So when you have rubber bands, bow and arrow, or any kind of like spring device, so as I pull it back, I'm going to have more elastic potential energy. When I release it, that potential energy becomes kinetic. If I want it to fly farther or have a greater speed, I have to pull back more because I have to have more of this to get more of this. So the more potential energy you have, the more kinetic energy you're going to have. Now, I could also theoretically increase the mass, but I really can't change the mass of the marble, right? I can't make the marble bigger. So it makes more sense just to pull back more so that you're storing more energy into the device. Therefore, when you release it, you're going to have a greater speed when it flies across the room. Okay? So here's another situation, same image, just looking at this, okay? So understanding mass and weight. If my mass is 600 kilograms, what's my weight going to be?
Wait, can I use a calculator?
Sure. You can also just roughly estimate.
60. Wait, 60.
What is gravity?
9.8.
It's 9.8. We can round 9.8 to 10, right? So if I have 600 kilograms, my weight is going to be somewhere around 600 newtons. Did you get the precise answer?
5,880.
Okay, so it's 5,880 exactly in newtons, or thereabouts, right? So what's my starting potential energy? Let's say that this height is 100 meters. If that's 100 meters, then I have to multiply weight times height. And that will give me 100 times 6,000. I'm going to add 2 zeros at the end. So I have 600,000 joules. All right? Now, to find, if I go 25% of the way down, so that's about right here. That's about 25% of what we have in this energy.
Good morning, 8th grade teachers. Please pick up your COGAT testing from Lab B if you have not already done so. 8th grade, please pick up your COGAT.
Alright, so when this begins to fall down, what is 25% of 600,000?
I'm sorry, that is Lab D as in dog. 8th grade, please pick up your COGATs from Lab D as in dog.
So here, again, I'm going to multiply that by 0.25, and then I'm going to find that it's going to have 150,000 joules. I write 150,000 joules equals half the mass, so that's half of 600 kilograms, times velocity squared. Now, when I have that, I can actually solve for velocity squared. All I have to do is isolate the variable, and then when I'm finished, find the square root of both sides, and it will tell me what my velocity is. Okay? So that's how you would solve that. Again, you multiply the total joules by 0.25 to find 25% of that. Okay? You're going to divide both sides by 300, and that will give you what velocity squared would be. Because half of 600 is 300. Okay? Interaction. So the molecule interaction during the heat transfer. Remember that with radiation, there's not really an interaction because there's no matter that's involved with that. There's no matter that's involved with that at all. With conduction, you have to be in direct contact. And with convection, just close proximity. So you do have to still interact with convection, but you just have to be close to the... Like, for example, boiling water over here cannot affect matter that's over there. However, if I have a space heater and that's heating up the air particles, they're going to move around the room a little bit. But if something is nowhere near the convection currents, there's not going to be any heat transfer at all. So conduction has to be direct contact, radiation is no interaction at all, and convection is going to be close proximity. During temperature changes, what is basically happening to the molecules that make up matter? Yes, sir?
They slow down when they get colder.
Right, so when something gets colder, they slow down, they lose speed. When it gets warmer, they're going to speed up. Because temperature is the average kinetic energy of particles that make up something, okay? Also know that when they get colder, they come closer together. And when they gain energy, they're going to expand. Now, with a solid, there are physical bonds that hold those molecules together. In a liquid, those are still present, but they're much weaker. And in a gas, they have been overcome. There are no physical bonds in a gas. Those have broken down altogether. Just understand some energy conversions here. A battery is going to be chemical to electrical. Hairdryer is electrical to thermal and mechanical. Okay? So energy conversions that take place in household appliances. You have energy conversions taking place in your cell phone. Just understand that when you change from one form to another, you do lose some of those joules of energy. Nuclear power. So we have large atoms that are radioactive. We split them apart in fission. When we do that, it gets really hot. It's basically a very miniaturized explosion that releases a lot of energy. This thermal energy from the reaction is going to cause steam to move through a turbine. Remember, when we spin a turbine, we can generate electrical power. So we go from nuclear to thermal, mechanical, electrical. You can write that down if you wish, but that's what's taking place when we have a nuclear power plant generating power. Okay?
Wait, what creates steam?
What creates steam is when the thermal energy is heating up water and the steam begins to move. Because it's not just steam, it's extremely hot steam. And it causes it to move through pipes and spin a turbine. Okay? Any other questions about this? All right. So again, convection. This is a great illustration. This is why it's easier. This is why, if you're in a burning building, the air in the top part is going to be really hot. Because remember, those warmer particles move up because they have less density. The colder particles move down because they have a greater density. Okay? When you're boiling something, again, you're going to have the warm ones move up and the cold ones move down. That's why it's even. That's why if you measure the temperature here, 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 it's going to be the same. It's because those moving currents make everything have an equilibrium. In the ocean, you have the hot on top, the cold on bottom. Okay? If you want to... you can have a really big temperature differential in just one area of water, depending on the depth. Yes, sir?
So if George has a can of Coke and he wishes to...
Okay, I cannot answer that question. That resembles a test question way too much.
If I
Think-
have a can of Coke and and my grandparents come over and they're really thirsty, but they only drink cold soda, so I really want to cool it down, should I put like an ice pack on?
Okay, so your question resembles a test question very closely. So all I can say is this, okay? I'm going to answer it to the best of my ability without being unethical. So, when you have conduction, you have direct contact where you're going to reach something close to a thermal equilibrium. In terms of the moving currents with a liquid or gas, remember that the warmer particles move to the top and the colder particles will circulate to the bottom. So I'm thinking that within a can of soda that you're going to have, because it is liquid, you're going to have a current moving within the soda. And that is all I can say. I do apologize. I wish I could tell you more, but it just resembles a test question very closely. So these graphs are actually very common. What it's showing you is you have a hot item and you have a cold item. So this is around 5 degrees Celsius and 7 degrees Celsius. And over time, what is going to happen is they're going to reach what we call a thermal equilibrium. Now, what does thermal equilibrium mean?
Same temperature.
Same temperature, exactly. So the hot one has to lose some energy, and the cold one gains some energy. Where does this get its energy from?
The hot one.
That one, right? This would be like if I handed you a bunch of candy and you gave half to your friend. In order for your friend to get some candy, you would have to lose some. Or you could use money or whatever you wanted to use for that. Insulators and conductors. Big idea here, guys. Thermal heat, specific heat capacity. Things that have a higher number are better at insulating because it uses a lot of energy for them to get hotter. Things that have a lower heat capacity are going to be conductors. If you're using something as a cooking utensil, you want to use something like wood or silicon plastic, something like that, because they're better insulators. They have a very high heat capacity. Using a metal spoon when you're making chili, the spoon's going to get hot and you're going to burn your hand. So just understand that the higher the number, the better it is as an insulator. Looking at specific heat capacity, the heat energy, this is the movement of thermal energy, that's what heat is mass times heat capacity times temperature change. So in this example, I have a material and it has a heat capacity of 200 joules per kilogram times Celsius. That means that for every kilogram I have and for every degree Celsius I want it to go up by, I have to give it 200 joules of energy, right? So setting this up, we have our formula, Q equals mc delta T. Again, that's mass, heat capacity, temperature change, and this is the quantity of heat, okay? So, if the current temperature is 20, and I want it to increase to 60, 60 minus 20 gives me an increase of 40. So delta T here is going to be 40 degrees Celsius. If my heat capacity is 200 joules per kilogram times Celsius, that goes right here. What is my mass? It says 3 kilograms. So all I have to do to find my energy is multiply 3 times 20 times 40. You want to go ahead and do that for me? 3 times 20 times, 3 times 200 times 40.
That's 24,600. 24,000.
24,000.
You guys said 24,000, but I want you to still put it in your calculator anyway to be sure. All right? So that's how much energy is needed. Again, this is joules. This is how much energy is needed to change that temperature. Okay? Again,